This is Knowledge Engineering with Semantic Web Technologies, lecture number 4, FOL Rules and Reasoning. And today we want to talk about rules, and we want to answer the question whether rules are more powerful, whether they are more than the description logics we already know. So, yeah, the problem here is, are description logics really enough? Are they sufficient? We know that more expressivity in logics usually also means more complexity, so we have to be careful, especially if it comes then to the question whether everything we define here might become undecidable. So we know too much complexity might lead to undecidability, so we know that already for first-order logic, of course. So now the question is, do we really need more expressivity than OWL-DL offers? It depends, of course, what you want to define, what kind of constructs you want to, for example, to design with your logic. So consider the following example. Let's say we have the following statement: a squanderer is a person whose expenses are higher than his income. Now your task would be define this with the help of a description logics. Okay, so let's have a look at the sentence. Okay, we have a class, a squanderer, and it's defined as a person. Okay, a squanderer is a person, that's easy. But the condition or the restriction we see here is really difficult because, yeah, he has probably two properties or roles that he's connected with. So he has expenses and he has income. But the problem is his expenses are higher than his income. And we have no idea how we should, in the end, somehow define this with the help of a description logic. So we can define that a squanderer is a person. We can also define that he has expenses, and we can define that he has an income. But to relate it in the way we do that here in natural language with the means we have right now is still not possible. So, and this simply also is a reason, for example, here classes and properties somehow are mixed up again in a definition and in a kind of that we cannot deal with, at least not right now within or with the help of description logic. So we will see whether we can do something about that. But of course, this lack of expressivity is one of the reasons why we are talking about rules, and we say rules are more expressive. Okay, so let's have a look at rules. But first, let's decide or distinguish between rules and semantic web. So usually in the semantic web, we concentrate on so-called declarative forms of knowledge representation, like the description logics, OWL or RDF. So we simply declare in a kind of way what exists, what not. It's not procedural. Rules, on the other hand, they are somehow procedural. You know this with if, then else or something. So this is a procedural kind of knowledge representation. And this usually also, of course, is used in knowledge engineering. So in expert systems, it is rather prominent. So they are rule-based systems, and then an entire knowledge base can be built up simply from rules. So for example, in Prolog, Clips, Jess, or OPS, which are examples for rule-based expert systems. So the point here is knowledge representation formalisms of semantic web. We know they have expressive limitations, and we assume that can be overcome by rule-based knowledge. So where we, for example, have the possibility also to compose complex classes from class and property expressions. So we can mix up somehow classes, properties. So the strict typing, especially when I combine them, has to be considered or has to be treated in another way like we do that right now in description logic. So therefore, let's have a look at rules first. What are rules? Yeah, everybody of us has seen rules. If you have seen a programming language, of course, then you have seen if A, if a condition holds, then something B will follow. So you can write this here as a simple implication in logics. If A, then B. A implies B. The interpretation of that rule, of course, always depends somehow on the context. So, for example, if you consider it as a general inference, then you have some premise, and from this premise there follows, or there is implied, a kind of conclusion. You can also see this as a hypothesis. So you have a cause, and the cause results in an effect. Or if you see it in a production environment, you have a precondition, and this condition in the end results in some kind of action. So it initiates a procedure. So how to deal with rules somehow is dependent of the context. And we have to consider different kind of rules. So for us, of course, logical rules are the most important rules, like for example here the first order logic implication. And for that, for the first order logic implication, so if F implies G, we know that this is equivalent, or there is an equivalent expression as a clause we see here as non-F or G. So this is a logical extension of the knowledge base, and usually we are dealing here, or we want to deal with an open world and in a declarative environment right now if we are dealing with description logics. With procedural rules or production rules, it's something different. So here, for example, if we are considering programming languages, we have a condition X. So if X, then Y, else Z. So this is dynamic. So here something can change in between. It means you have executable machine instructions which are connected to the rule. And this is some kind of an operational semantics here for procedures. So we do not consider that. And also in the traditional logic programming based expert systems or knowledge bases, also their rules work a little bit different than we want to deal with them in our open world. So usually there we have a closed world, it's semi-declarative, and you see here also the rules are usually stated or expressed in a little bit other way, so it's reversed somehow. First you have the head of the rule, so what's the outcome? The implication arrow is vice versa, it points in the other direction, and then you have the precondition or the body. So this means a person who is not a man is a woman. Yeah, but in a closed world, so you have not the possibility to assume the existence or to hypothesize about the existence of an individual which is not there in the beginning, and you cannot take it ad hoc from somewhere like you do this with existential quantification in our world, in the open world. So we want to consider logic rules. Okay, so first let's consider first order logic rules. Okay. Rules are nothing else but first-order logic implications, and these are so-called horn clauses. We will talk about horn clauses now in depth a little bit more. So usually you see that. So you have here a body, which is the first part of a rule, and these are conditions a sub 1 to a sub n, and they are all somehow connected in a conjunctive way, and they imply some implication. So a header would be there. And this, of course, can be logically transformed in an equivalent expression that you see here in a clause. And if you do that, then from this a sub 1 and a sub b and so on, a sub n implies h, there becomes then not a sub 1 or not a sub 2 and so on, or not a sub n or h. And this is a clause, and you see everything from the body here is negated, and of course the connector is reversed. And then, of course, the implication is transformed into a disjunction, and therefore we end up in a clause where the first part is negated and the implication part is as it is. So this would be a semantic equivalent horn clause. Usually you omit the quantification there because all three variables that you see here are considered to be universally quantified. It means the rule holds for all possible assignments. Therefore, we do not consider quantifiers usually here in the rules because they are considered universally. Okay, sometimes you might see these rules also written the other way around, like in the logic programming-based systems, as we see here, that the head stands first and then comes the body, but you can simply distinguish them because the implication arrow here points in the other direction, as you see here. So this is the other way of a rule. Sometimes in the header part, there can be multiple elements. So if there are multiple elements, they are usually also considered to be conjunctively combined together. So this would be h sub 1 and h sub 2 and h sub 3 and so on and so on. And there is a nice transformation. It's called the Loy-Topor transformation. And with that, you can say, okay, this expression that you see here, the upper one, where in the head part are multiple formulas, this is equivalent to a conjunctive or to the sum of single rules which only have one of these header elements in their head. So here, what you do here, you decompose here the compound in the head to be the implication of a single or an atomic value here. And this is the Loyd-Topor transformation. So you can deal with these kind of rules quite easily. Then there is a kind of special rules which are called disjunctive rules. There you have to consider a header, where in the header all the elements are not connected conjunctively but disjunctively. So the question is, how should this be then interpreted? So this is kind of a reverse implication. So this means something like, if I see something, then the light is on or the sun is shining. So you can also read this as if-then, but you connect then the precondition as the outcome of your rule. So if I see something, then some precondition or something must hold, like then the light is on or the sun is shining. So these are so-called disjunctive rules. Okay, there are more variants that we have to consider. So in general, these rules are considered as clauses which are disjunctions of atomic formulas or negated atomic formulas. So we do not take care where something is negated or something is not negated. But Horn clauses are for us the most interesting one, because a Horn clause is a clause which has at most one negated atomic formula. So, and this, of course, you can see if you have a non-negated implication, so a non-negated rule, and you translate this then into the clausal form, you see that the entire first part, the body of the rule, then is negated, and only the header is non-negated. So we have exactly one element which is not negated. And this then would be a Horn clause. If exactly only one is negated, and not only at most one, then we have a so-called definite clause, which is a subclass of Horn clauses. And you can also have effect. So this is a single non-negated atom. Then we say simply state effect. This is not a rule. This holds. This is true. So effect, a single non-negated atomic formula. Okay, so let's have a look at a few examples. It's much more easier than you think. So this is a clause. What does this say? So a person is either a woman or a man. So this is a disjunctive clause. Pretty easy. This is not a Horn clause, because we have, if we translate this in clausal form, it would have two non-negated atomic formulas, women and man. And of course, then it's not a Horn clause. Let's look at the next one. We say here X is a man and X has a child Y, then X is a father. And this is a definite clause because we have exactly one non-negated atomic formula within the clausal form of that. So clausal form, you would see the first part would be negated, so everything which is in the body. Only the header would not be negated, only one element in the header, therefore this is a definite clause. It's also a Horn clause, but it's more special, it's a definite clause. Next one here, it's also interesting, would also be a clause. Here we have combined expression. We have a predicate has brother, and this is combined with a unary predicate, which is a function here, mother of X and Y, and of course the brother of the mother of Y. If Y is the brother of the mother of X, then Y is the uncle of X. This is the way how it works. And mother here is in blue. It's a so-called function symbol. So you have to treat functions of all the predicates that exist here in first-order logic in a special way. This is quite of important if we later on want to restrict rules to maintain decidability. Then these function symbols or functions have to be considered in a special way. But up to now, it doesn't matter anyway. This is only a variant of a first-order logic rule. Let's look at the next one. This is interesting simply because the header element is empty. So this is null or zero, which means if X is a man and X is a woman, then, so you cannot imply anything from that. So because it's not possible that both is true. So this something says something like the class man and the class woman, they are disjunctive somehow. But this is a horn clause because it says only at most one variable in the clausal form must be or can be positive, and there no variable is positive in the clausal form. Therefore, it's a horn clause. And this one, the last one, it's simply an atomic formula. So Anya is a woman, so Anya belongs to the class woman, and this is a fact. So these are single variants of first-order logic rules, and you will see more of them in the exercises. So let's go to our example that we had in the first place. So consider the following example. A squanderer is a person whose expenses are higher than his income. Now, are we able to express this with a rule? Yes, we are. Just look at the following. So we say X is a person, and we say X has the income Y. And we say X has the expenses Z. And then we say Z should be greater than Y. And if all these conditions hold, then X is a squanderer. So we define classes, new classes, here the class is squanderer, with the help of a rule. And in the rule, we are able to combine class expressions and, at the same time, property expressions. And this, of course, is much more powerful than, for example, what we can do with description logics. The point, of course, you might say, okay, how do I get this arithmetic Z is greater than Y somehow into my logical framework? You could define a predicate, for example, which says greater than, and then, of course, the interpretation of that property would somehow be equivalent to the arithmetic that is behind that. So then would this problem also be solved? So these are rules. Okay, so now let's somehow compare description logics with rules. So rules usually are usually considered to apply only to known constants. So my entire universe is known beforehand. It's not possible to create new things on the fly with the help of existential quantification, because here we don't have existential quantification. All variables that you see are not quantified, which means they are considered to be universally quantified. So something like that, for example, if I do in description logics define a human as somebody whose parents are human, this would imply that, of course, if I have something in the class human, then I would automatically deduce that this human has a human parent too, and so on and so on and so on. So therefore, I could here on the flight create new individuals, and this is not possible in the rules world. So if rules are considered as first-order logic formulas, of course, if I then combine them, first-order formulas and ALC, so as our description logics, this would lead to undecidability. So, of course, we have more expressivity, but on the other hand, it's first-order logic, so therefore it's undecidable. So what you have to do is somehow you have to try to find restrictions for rules that we can somehow keep or maintain decidability. And if you consider rules only and do not consider description logic on the first hand, there is something or some restriction to rules which is called DATALOG, which is a programming language which builds upon first-order logic rules with some restrictions, and these restrictions maintain decidability. And I want to show you a little bit of DATALOG today, but only just for information. So DATALOG is quite interesting. It has been developed in the late 1970s, so as a foundation for so-called deductive databases. And usually DATALOG is a logical rule language that consists of horn clauses without function symbols. So we don't consider function symbols here. This also has a reason. Simply, if I really use function symbols and they, for example, they also include basic arithmetics, then I have a problem simply because there is also an infinite number of equivalent expressions that should have to be considered. And usually these logic programming language where I can do logic on these rules, they decide about equivalence usually by simple pattern matching. And then this would, of course, be not solvable. Therefore, we don't consider function symbols here. But what is allowed are conjunction, constants, universally quantified variables, and predicate symbols. Sure. What is not allowed are disjunction, negation is not allowed, existential quantification, already we know that is not allowed, and function symbols are not allowed. The nice thing is, if you restrict to that subset of available first-order logic, then what you have as a result will be decidable. And not even that, it's also computationally efficient. It means so you can, for example, calculate satisfiability and stuff like that in exponential time, so which is, for logic, quite fast. Okay, so let's have a look at a few examples. So first, DATALOG syntax. First, we talk about terms in DATALOG, which are either constants or variables. And then atoms usually are predicates over so-called terms, so over constants and variables. And from these atoms, usually you construct your rules, where you say over all variables x sub 1 to x sub n, so this is universally quantified. Then you have your rule, which consists of atoms, and you have here also a body part and a header part. And these are usually only Horn clauses. And then, of course, a DATALOG program is nothing else but a set of DATALOG rules. And with these kind of rules that are restricted to the operations we have seen already on the last page, you are already able to define things which are much more complex than, for example, we can define in description logic. But it's still decidable, which is a nice thing. So this is a nice modeling language. Let's have a look at a few examples here. So, for example, I could say, yeah, if X is a vegetarian and Y is a fish product, then X dislikes Y. So what we do here, for example, is we define a new property, dislikes, with the help of two classes that we combine with each other. It's nice, isn't it? Sure. What else can we do? The other way around. So here I can define a class with the help of two properties. So I can say, if X has ordered the dish Y and X does not like Y, then X is unhappy. So this is also nice. Let's have a look at the next example. I also can say, if X has ordered Y, then Y is a dish. So here we have defined a class simply with the help of a property. So more complicated. So for example, if X dislikes Z and Y is a dish which contains Z, then X dislikes Y. You see, these expressions can become rather complicated, although we are restricted to a few logical connectives and things that are allowed in DATALOG. So also here I can state that, for example, that Matthias must be a vegetarian. This is also a DATALOG statement in that sense. Or I can say here, for example, X is happy and X is unhappy, and this of course results in an empty set, which means you can not be happy and unhappy at the same time. So this shows a little bit of the semantical expressivity of DATALOG. So DATALOG rules allow the mixing of classes and relations, so of unary and binary predicates. That's quite nice. Therefore, it's more expressive than a description logic. And for example, if you combine DATALOG with OWL, this results in the so-called Semantic Web rule language, which is part also of the Semantic Web technology stack, but you have to keep in mind if you did combine both then, so if you take full expressivity of OWL, so OWL classes in that sense, and take full expressivity of DATALOG, both together you end up in something which is in the end not decidable, but nevertheless you can work with it. Okay, so now you have seen something about rules, and we have come almost to an end of the entire lecture. So we have talked about knowledge construction, the definition of models, of knowledge representation with the help of OWL and the description logics behind that. And today we have talked about rules, which are even covering more expressivity than previously considered in OWL. In the next and the last part of the lecture, we want to take a look how this works if we apply this on a practical example. And I will show you a little bit how it is to work with an ontology editor, and we can do some live editing of OWL ontologies and rules.